In the wild, living plants are incredibly fragile. Their defining features, the precise color of a petal, the curve of a leaf, the structure of a bloom, fade, wilt, and drop in a matter of days. To study the natural world, early explorers and botanists had to figure out a reliable way to hit pause on that rapid decay. The first step was physical extraction. Collectors would carefully sever a wild specimen in the field while it was still vibrant and full of moisture. Immediately after cutting, they clamped the plant between sheets of unprinted newsprint and felt blotters, locking it tight inside a heavy wooden field press. This intense pressure forces the moisture out of the organic tissue, preventing rot. The result is a permanent physical archive known as an herbarium. An herbarium is a repository of carefully dried and preserved plant specimens used for scientific study. This image reveals what that physical reality looks like. The basic anatomical structure is crushed flat, and the dried organic material is secured to archival paper with small strips of tape. The literal organic matter survives, but the three-dimensional architecture of the plant is destroyed, and its living color is entirely drained away. Scientists needed a secondary, visual method to capture these species exactly as they lived. We can trace the origins of that visual method back centuries to dark, candlelit studies where the earliest written records of plant life were kept. Botanical illustration began with the urgent medical necessity to accurately distinguish a healing root from a lethal poison. This ancient manuscript, the Vienna Dioscurides, is one of the oldest surviving manuals of this kind. The Vienna Dioscurides is an early 6th century illuminated Greek manuscript that catalogs hundreds of plants and their medicinal properties. But there was a fatal flaw in the system. Scribes copied these drawings from older books, rather than looking directly at actual living plants. Over centuries of repeated copying, the illustrations drifted from reality, becoming dangerously abstract and highly stylized. This severe degradation of medical knowledge forced Renaissance scientists to abandon the ancient copies. They went back outside to draw directly from the meticulous observation of nature, sparking the true birth of botanical illustration. The actual work of illustration happened far from the muddy fields, shifting to quiet, sunlit studios dedicated to precise tactile study. Artists often painted on specially prepared calfskin known as vellum. Its smooth, non-porous surface allowed paint to sit completely on top, creating a luminous effect that mimicked the glowing translucency of a living flower petal. They layered nature-derived historical pigments onto this surface. They extracted bright, transparent yellow from the gamboge tree resin of Southeast Asia and sourced warm brown sepia ink directly from the ink sacs of cuttlefish. Armed with these exact materials, the illustrator was doing something conceptually different from what a modern digital camera does. This split-screen diagram illustrates the distinction. On the left, a photograph captures a holotype. A holotype is a single, specific physical specimen used by scientists to formally describe a species. If you photograph one, you record individual flaws, like accidental insect damage. The illustrator, however, aims for the archetype on the right, synthesizing shared traits from dozens of flawed plants into a single, perfect biological blueprint. The illustrator reconstructs the idealized truth of nature's design by synthesizing multiple specimens into a single biological blueprint. Pushing this meticulous craft forward required a few specific visionaries who were willing to venture out into the wild and take exhaustive field notes. The Austrian natural history painter Ferdinand Bauer faced a major hurdle on his expeditions. The plants he collected would wilt and lose their vibrant colors long before he could return to his studio to paint them. To solve this, Bauer invented an ingenious numerical color code system. He made rapid pencil sketches in the field, assigning specific code numbers to every hue, allowing him to perfectly replicate the living colors years later. A century earlier, the German artist and scientist Maria Sibylla Merian stopped drawing isolated dead plants entirely choosing instead to capture living ecosystems. This 1705 illustration by Marion depicts insects actively feeding on their host plants. By proving insect life cycles were tied to the plants they consumed, Marion dismantled spontaneous generation, the ancient theory that insects magically sprang from mud. Through Bauer's precise color data and Marion's dynamic ecosystems, these pioneers transformed botanical illustration from simple cataloging into a complex, rigorous science. In the modern world, botanical history is stored in massive, climate-controlled herbarium vaults. This silent library forms an active, vital database, containing millions of historical illustrations and pressed specimens. Modern scientists rely on these centuries-old visual records to identify critically endangered species and to accurately track the ecological shifts driven by climate change. The ultimate advantage of the botanical illustrator remains exactly what it was 300 years ago. They possess the unique ability to edit out the chaotic, tangled background of the wild to emphasize pure diagnostic features. This diagram shows how isolation works. An artist can magnify specific internal structures, like dissected reproductive organs, displaying them simultaneously on a single page. This curated detail provides a structural clarity no single photograph could ever offer. Because this practice relies entirely on visual anatomy rather than technical jargon, it acts as a universal scientific language, legible across centuries and cultures. Botanical illustration is ultimately an act of profound care, the quiet discipline of looking at a fragile piece of the world closely enough and patiently enough to truly see it.